The National Electrical Code, or NEC, specifically prohibits splices in panelboard gutters when these gutters are used to reach circuit breaker terminals. This prohibition is explicitly stated in NEC Article 384.29, which reads, "Conductors shall not be spliced in the panelboard gutters." While the NEC itself does not provide a specific rationale within the codebook for this prohibition, the UL standards for panelboards, specifically UL 67, offer several reasons that underscore the importance of this rule. Firstly, safety is paramount. Splices, by their nature, can introduce potential points of failure in an electrical system. A poorly executed or inadequately protected splice can become a source of arcing, overheating, or even electrical shock. Furthermore, splices can sometimes reduce the effective current carrying capacity of a conductor if not properly made and maintained. This reduction in capacity can lead to overloading of the conductor, increasing the risk of insulation breakdown and fire. Secondly, wire fill is a critical consideration. Panelboard gutters are designed to accommodate a specific volume of conductors. Splices inherently increase the overall wire volume within the gutter. When splices are introduced, they can cause the gutter to exceed its approved wire fill capacity. Overfilling a gutter can restrict airflow, leading to increased conductor temperatures and a heightened risk of fire. Also, overcrowding makes it difficult to properly manage and organize the wiring, potentially causing damage to the insulation and increasing the risk of short circuits. Thirdly, maintenance and troubleshooting are significantly impacted by splices. The presence of splices in a panelboard gutter can make it considerably more difficult to remove or replace conductors. This can impede routine maintenance, troubleshooting, and any necessary repairs. The added complexity of dealing with splices can increase the time required for these tasks and raise the likelihood of errors. When conductors need to be traced or replaced, splices create additional points of connection that must be examined and potentially disconnected, making the process more cumbersome and time-consuming. Given these concerns, it is important to consider alternatives to splicing conductors in panelboard gutters. There are several viable options that can ensure code compliance and maintain the integrity of the electrical installation. One option is to use a solid conductor of sufficient length to reach the circuit breaker terminal. By using a continuous unbroken conductor, the need for splices is eliminated altogether. This approach provides a more reliable and safer connection, reducing the risk of failures associated with splices. Another alternative is to use a wireway or junction box outside the panelboard to accommodate any necessary splices. These enclosures are specifically designed for making electrical connections and provide ample space for splices without compromising the wire fill requirements of the panelboard gutter. Using wireways or junction boxes ensures that splices are properly contained and protected, minimizing the risk of electrical hazards. A further option is to use a circuit breaker with a built-in terminal that allows for direct connection of the conductor. Some circuit breakers are designed with extended terminals or connection points that can accommodate longer conductors without the need for splicing. This approach simplifies the wiring process and reduces the number of connections required within the panelboard. Finally, consider using a panelboard with a separate wiring compartment or gutter specifically designed for splices. Some panelboards are manufactured with dedicated compartments or gutters that are separate from the main section where circuit breakers are installed. These compartments provide a safe and organized space for making splices, while ensuring that the main panelboard gutter remains free from obstructions. By adhering to NEC Article 384.29 and considering these alternatives, electrical installations can be made safer, more reliable, and easier to maintain. These practices help to minimize the risk of electrical hazards and ensure the long-term performance of the electrical system.